hidden labs, silent experiments, projects that shaped technology without ever reaching the public eye. Today, we uncover 100 facts about secret government projects, real research, strange discoveries, and forgotten innovations that quietly changed how the world works. No drama, just the science, the mystery, and the truth behind closed doors. Chapter 1. People often imagine secret government projects as science fiction, but many started with simple questions. What can humans truly build? Early programs focused on silent aircraft, coded communication, and remote sensing. Records show teams testing metal alloys that could survive extreme pressure, hinting at ideas far beyond normal engineering. These projects shaped the earliest blueprint of modern covert research. Chapter 2. One declassified report describes engineers studying unusual atmospheric signals. They believed certain radio waves could bounce off hidden layers in the sky. This led to experiments that mapped weather patterns more accurately than public systems. While innocent on the surface, the same tech was rumored to track unidentified aerial movements, mixing climate science with strategic surveillance. Chapter 3. A quiet project in the 1960s explored how human reflexes respond under sensory overload. Scientists pushed pilots into rapid shift simulations to test survival thresholds. They learned the brain adapts faster than expected when facing sudden danger. These findings later shaped high-speed aircraft programs and raised questions about whether humans could handle vehicles beyond traditional limits. Chapter 4. Intelligence agencies spent years studying micro-drones before the public even knew the word. Early prototypes looked like insects, powered by tiny motors and heat-sensitive wings. They were unstable but groundbreaking. Reports state their purpose was simple: observe without being seen. The science behind their movement came from studying real insects, merging biology with engineering. Chapter 5. A classified medical program tested how long memory holds under stress. Volunteers solved puzzles while exposed to pressure changes, sound waves, or rapid light pulses. The goal was to understand how soldiers recall critical data in chaos. Results suggested short bursts of stress actually sharpen memory, surprising researchers and inspiring new training methods. Chapter 6. During the Cold War, researchers examined whether metal structures could deflect certain frequencies. They built odd geometric frames designed to bend signals. While these didn't create invisibility, they reduced detection range. This concept later evolved into stealth technology. The original tests, though simple, revealed how much physics could be manipulated with precise angles. Chapter 7. Documents mention a program studying deep ocean pressure tolerance. Scientists lowered reinforced capsules into trenches, measuring how materials deform under tons of force. They discovered combinations of titanium and ceramic survived longer than expected. This led to improved submersible shells and raised curiosity about what might be reachable at ocean depths, previously considered impossible to explore. Chapter 8. A less-known project focused on rapid-response satellites. These small units were built to launch quickly and operate for short missions. Engineers used lightweight composites and compact fuel packs. Their orbits could shift faster than standard satellites, allowing quick observation of global events. The tech later influenced modern emergency communication systems. Chapter 9. Scientists once tested whether plants react to electromagnetic fields. Sensors attached to leaves recorded tiny electrical changes when exposed to controlled signals. The goal was agricultural optimization, but rumors suggested intelligence agencies wondered if plants could detect movement or environmental shifts. While far-fetched, the data proved plants are more electrically active than expected. Chapter 10. Reports confirm a project examining human heat signatures. Researchers mapped how the body emits infrared patterns under different emotions. Anger, fear, and calm states produced distinct temperature maps. This helped develop early thermal imaging tools. Though intended for rescue operations, the tech also offered advantages in tracking hidden subjects at night, blending psychology with physics. Chapter 11. A classified aviation program explored how wings behave at near-space altitude. Engineers tested thin carbon layers that resisted freezing and vibration. The aircraft never reached full production, but its experiments revealed how air density changes control surfaces. These insights guided later high-altitude reconnaissance vehicles, proving small physics details can decide whether a mission succeeds or fails. Chapter 12. Another program focused on sound suppression. Researchers tried shaping exhaust trails to break up noise waves before they traveled. They discovered certain cone patterns reduced engine signatures dramatically. Though designed for stealth aircraft, the same principle influenced modern silent wind turbines. The project quietly showed how manipulating vibration can change what the human ear detects. Chapter 13. An intelligence lab studied how magnetic fields affect digital storage. Scientists exposed prototypes to controlled magnetic bursts to measure corruption levels. The results helped them design secure hardware that resisted tampering. These early tests shaped future encrypted devices, proving that physical science, simple magnetism, was just as important as advanced code in protecting critical information. Chapter 14. A covert research team explored rapid blood-clotting compounds for field emergencies. They mixed minerals with protein-based gels, aiming for instant wound sealing. Trials revealed one formula that solidified within seconds when exposed to oxygen. Although not widely released, this breakthrough paved the way for modern trauma packs used by rescue units today. Chapter 15. A forgotten space project investigated reflective shields for solar flares. Engineers tested mirror-like materials that deflected bursts of charged particles. The goal was protecting satellites during storms. Some prototypes partially worked, suggesting certain alloys could redirect energy rather than absorb it. These findings quietly influenced the way current satellites are armored against cosmic radiation. Chapter 16. In a remote desert facility, researchers studied ultra-long-distance radio communication. They tried bouncing signals off naturally ionized clouds. Testing proved the atmosphere sometimes acts like a giant mirror, allowing transmissions to travel far beyond normal range. This became the foundation for backup communication systems used when satellites fail or during global emergencies. Chapter 17. A project called Night Pulse analyzed how animals navigate in darkness. Scientists tracked bats, owls, and deep-sea fish, comparing their sensory patterns. They learned these animals rely on micro-vibrations and magnetic cues. This knowledge later supported the development of low-light sensors and motion detection radars, all inspired by natural survival abilities refined over evolution. Chapter 18. One government lab tested ultra-fast desalination using electrical pulses. Water flowed through charged membranes that separated salt instantly. The technology was promising but expensive. Still, the research proved electricity could manipulate water molecules more efficiently than pressure alone. This shaped modern portable purification systems for disaster relief teams and remote operations. Chapter 19. A small team studied how dust interacts with light at extreme speeds. They fired tiny particles across vacuum tubes and tracked their glow under lasers. Data showed dust carries static charges that change brightness patterns. These insights were later used to improve early warning systems for meteor trails and high-speed debris near spacecraft. Chapter 20. Researchers explored how brainwaves shift during rapid decision-making. Volunteers face-timed logic tests while sensors mapped neural spikes. Patterns emerged. The brain creates a priority wave seconds before choosing. This discovery helped refine pilot training simulations, making them more realistic. The study showed how understanding simple neural timing can improve complex human performance. Chapter 21. A covert engineering group tested flexible armor using layered fibers inspired by spider silk. They discovered certain weaves could absorb impact by spreading force across micro-strands. While the armor wasn't perfect, it was far lighter than metal plates. This research later influenced modern protective gear used in dangerous field missions, proving nature-based design can outperform heavy machinery. Chapter 22. A hidden geological project studied underground resonance. Scientists placed sensors deep in caverns to track how vibrations travel through rock. They learned some formations naturally amplify sound, acting like giant echo chambers. This helped intelligence units detect distant movements and map tunnels without physical entry, using nothing more than controlled pulses and physics. Chapter 23. A rarely mentioned program worked on ultra-durable batteries. Researchers used crystal-based structures to stabilize energy flow. Tests showed these prototypes held charge far longer than standard cells. Though too costly for mass use, the experiment influenced modern long-life power packs used in remote sensors, where reliability matters more than production price. Chapter 24. A secret marine study examined bioluminescent organisms. Scientists collected glowing plankton to understand how they produce light without heat. The discoveries helped engineers design low-energy signal markers for underwater missions. These soft glows allowed divers to communicate silently, inspired by creatures that evolved illumination millions of years before electricity. Chapter 25. A medical project explored controlled hypothermia for survival. Researchers tested how lowering core temperature slows cellular damage. They found a narrow threshold where the body enters a stable, low-energy state. This knowledge was later applied in emergency procedures to protect patients during critical transport or surgery, extending survival windows once considered impossible. Chapter 26. Engineers once attempted to build a drone that could ride thermal air currents like birds. They studied how wings tilt during rising heat columns. Early prototypes drifted unpredictably, yet the data revealed how natural airflow can reduce fuel use. These insights influenced high-endurance drones capable of staying airborne longer with minimal power. Chapter 27. A psychological project tracked how isolation affects time perception. Volunteers lived in controlled rooms without clocks. Scientists found people naturally shorten or lengthen internal timing depending on light exposure. These results helped design stable environments for submarine crews and space missions, where losing track of time could disrupt decision-making and mission flow. Chapter 28. A covert chemistry team tested new smoke compounds that dispersed into ultrafine particles. These clouds scattered light more efficiently, creating thick cover with small amounts of material. Though invisible on radar, they created visual barriers that confused tracking systems. The research shaped modern concealment tech for rapid field operations. Chapter 29. A project known as Silent Line studied how electrical currents travel through wet soil. The team discovered certain mineral-rich layers carry signals farther than expected. These findings helped develop ground sensors that detect movement or equipment vibrations without direct contact, turning the Earth itself into a listening device powered by simple conductivity principles. Chapter 30. Scientists ran tests on micro-explosive bolts meant for spacecraft separation. They measured how small charges can break heavy structures cleanly without shock damage. The work refined timing circuits to millisecond precision. This technology later enabled safer satellite deployment, showing how controlled force can create delicate results in extreme environments. Chapter 31. A classified vision study explored how eyes track fast-moving shapes. Scientists used rotating lights and sudden flashes to map reaction accuracy. They learned humans predict motion slightly before it happens, creating a natural anticipation curve. This helped improve pilot helmets and targeting displays, making fast data easier to read under pressure. Chapter 32. A weather control research unit tested cloud seeding mixtures designed for rapid dispersal. Early trials showed some formulas triggered rainfall faster than standard methods. Although results varied, the findings revealed how tiny particles influence atmospheric charge. This knowledge quietly shaped modern storm modification studies, blending chemistry with environmental physics. Chapter 33. A transportation project studied magnetic uplift on lightweight rails. Engineers tested coils that levitated small metal carriers. The system wasn't stable for public use, but it proved frictionless travel required less energy than expected. These early lessons influenced future high-speed transport concepts powered by magnetism rather than wheels. Chapter 34. A biology program analyzed heat-resistant microbes found near volcanic vents. Scientists isolated proteins that helped these organisms survive extreme temperatures. Their discoveries guided the creation of durable enzymes used in field kits for rapid testing, allowing samples to stay functional in harsh climates where normal materials fail. Chapter 35. A space defense team studied tiny meteor fragments under controlled collisions. They used high-velocity launchers to recreate impacts on metal panels. Data revealed that angled surfaces deflect damage better than thick armor. This principle later influenced spacecraft shielding, proving geometry can protect more effectively than brute strength. Chapter 36. Researchers examined how ultra-fast cameras capture electrical arcs. By slowing frames to millionths of a second, they mapped how lightning-like currents branch. Understanding these branching patterns helped engineers design safer grounding systems. It also improved early warning sensors that detect sudden charge buildup before equipment overloads. Chapter 37. A neuroscience project explored how scent affects alertness. Volunteers inhaled controlled chemical blends while completing puzzles. Tests showed certain aromas sharpened focus, while others calmed the nervous system. These findings shaped covert kits for alertness control during long missions, proving simple environmental cues could shift mental performance. Chapter 38. A small engineering group tested liquid metal circuits that reshaped under magnetic fields. These flexible pathways repaired minor breaks automatically. While unstable for mass production, they hinted at future self-healing electronics. The research demonstrated how metals behave like fluids under specific forces, merging physics with emerging robotic concepts. Chapter 39. A hidden ocean program studied deep current mapping. Sensors dropped into trenches revealed narrow highways of fast water flow. These currents could move equipment silently across long distances. Naval units later used this knowledge for stealth deployment, riding natural forces instead of engines to reduce detection. Chapter 40. A classified optics lab tested lenses that shift transparency when voltage changes. These lenses adapted to glare, darkness, or sudden flashes in milliseconds. Originally designed for pilots, similar tech later reached civilian smart glasses. The science showed how electric fields can alter light flow instantly, giving users dynamic vision control. Chapter 41. A covert aerospace group researched silent rotor systems. They tested blade shapes that split airflow into smaller streams, reducing vibration and noise. While early models still hummed, the data helped design quieter helicopters for discrete missions. The project proved that slight angle changes can dramatically alter how air pressure moves around spinning surfaces. Chapter 42. A biomedical unit explored rapid muscle recovery gels. Scientists studied how certain minerals interact with tissue under microcurrents. One formula showed accelerated healing in controlled trials. Although not released publicly, the research influenced modern field patches that reduce fatigue for soldiers and rescue teams operating in harsh conditions. Chapter 43. A physics-focused group investigated low-energy plasma rings. They tested chambers where ionized gas formed stable loops for a few seconds. These rings offered insight into how magnetic fields control charged particles. While not weaponized, the findings helped improve high-temperature sensors and advanced lab equipment used to study extreme environments. Chapter 44. An underwater robotics project tested machines that mimicked fish movement. By copying fin angles and muscle patterns, engineers built drones that moved quietly through water. These prototypes blended biology with mechanics, creating motion patterns nearly indistinguishable from sea life. This allowed silent observation in areas where propellers would reveal activity. Chapter 45. A cognitive research team tracked how people process mirrors and reflections. Volunteers solved tasks while images flipped rapidly. Results showed the brain builds a mental reference map before reacting. This insight guided visual recognition systems, making them better at identifying reversed or distorted shapes during surveillance. Chapter 46. A materials program experimented with vibration-damping foam used in high-impact environments. The foam absorbed shock by compressing microscopic air pockets. Tests revealed a specific density that protected sensitive instruments during transport. This led to safer storage for delicate equipment used in covert missions and space launches. Chapter 47. A classified astronomy group studied small flashes on the lunar surface. These transient events occurred randomly. Scientists suspected micrometeors or static discharge. By tracking them, they improved early detection systems for incoming space debris. The project blended observation with physics to understand how even tiny impacts affect long-term exploration. Chapter 48. A neural mapping project examined how music rhythms affect stress levels. Volunteers listened to varied beats while sensors tracked heartbeat and electrical activity. Steady patterns reduced cortisol spikes, while chaotic rhythms sharpened alertness. These findings shaped sound-based focus tools used in training environments where emotional control affects performance. Chapter 49. Engineers explored ultra-thin solar films that worked under low light. They tested layers of semiconductor dust fused onto flexible sheets. Even weak illumination produced measurable energy. This research later influenced emergency gear powered by ambient light, useful in locations where traditional panels fail. Chapter 50. A secret communication project studied laser signaling through fog and smoke. Tests showed certain wavelengths cut through heavy particles better than others. With precise calibration, messages stayed readable in conditions that normally block light. The discovery helped create reliable optical systems for operations where radio silence is necessary. Chapter 51. A classified nutrition lab studied compact energy bars for extreme missions. Scientists tested blends of fats, grains, and slow-release compounds. One formula kept subjects alert longer without sugar crashes. Though simple, the research shaped modern ration packs used in cold, high-altitude, or underwater operations where consistent energy can decide mission success. Chapter 52. A geology-based project placed sensors along fault lines to measure microquakes invisible to standard tools. They discovered patterns that preceded small shifts, revealing how stress travels through rock. These insights improved underground facility design, allowing structures to stay stable during subtle Earth movement that would normally go undetected. Chapter 53. Researchers experimented with low-light algae that glow under specific frequencies. They learned the organisms respond to tiny chemical changes in water. This made them useful as natural detectors for underwater contamination. Though simple biology, the idea turned living cells into quiet monitoring tools for sensitive marine zones. Chapter 54. A covert physics team explored how thin wires behave under rapid temperature swings. Some alloys expanded unevenly, creating tiny mechanical pulses. These pulses became the basis for micro-actuators used in precise instruments. The project showed that controlled heat variation could generate movement without motors, opening new paths for silent mechanical systems. Chapter 55. A psychological study tracked how people react to repeating patterns. Volunteers viewed shifting shapes while signals recorded their attention peaks. Results suggested the brain predicts repetition faster than random motion. This knowledge refined interface designs for surveillance analysts, reducing fatigue by aligning visuals with natural human pattern recognition. Chapter 56. An engineering group tested self-cooling fabrics woven with conductive threads. When exposed to heat, the threads dispersed warmth across the material. This kept internal body temperature steadier in high-risk missions. Though the technology stayed restricted, it influenced later designs in temperature-regulating gear for extreme climates. Chapter 57. A satellite project examined compact thrusters that used ionized gas. Despite low force, their efficiency allowed long-duration orbit adjustments. Early units proved stable under constant operation, influencing modern maneuvering systems that keep reconnaissance satellites aligned even when external conditions shift. Chapter 58. A hidden audio research team explored how low-frequency waves move through buildings. Tests showed some materials amplify bass vibrations more than others. The findings helped engineers design rooms where sensitive equipment stayed stable, even near loud machinery, by shaping walls to redirect disruptive frequencies. Chapter 59. A medical unit tested how microdoses of certain vitamins affect night vision. Controlled trials showed slight improvements in low-light clarity when combined with specific amino acids. While the effect was modest, it supported specialized diets for personnel operating in darkness without relying on bright equipment. Chapter 60. A robotics division experimented with soft grip manipulators that used air pressure instead of metal joints. These flexible arms handled fragile objects without crushing them. The project revealed how pneumatic systems mimic natural muscle movement, leading to tools capable of working silently in confined or hazardous environments. Chapter 61. A covert climate lab studied heat pockets forming above large cities. Using airborne sensors, they tracked rising warm columns that shifted local wind patterns. The data showed urban layouts change airflow more than expected. These findings shaped strategic planning for drone routes and emergency aircraft, using natural temperature differences to improve stability. Chapter 62. A research team examined how thin ice fractures under pressure. They created controlled cracks and filmed ripple speeds across the surface. The patterns helped predict break points, allowing safer operations in polar regions. Their work also improved structural testing for lightweight materials that behave similarly under sudden stress. Chapter 63. A chemistry unit developed ultra-stable paints that reflect infrared light. These coatings reduced heat signatures when applied to surfaces. Tests revealed certain particle shapes scattered thermal energy more effectively. This discovery guided camouflaging methods for equipment used in hot environments where infrared detection is common. Chapter 64. An advanced vision program studied how insects respond to polarized light. Tiny sensors recorded their flight corrections when exposed to shifting patterns. Scientists used this to enhance navigation systems that operate without GPS. The idea came from the sky's natural polarization map, invisible to humans, but a clear guide to many animals. Chapter 65. A secret medical project tested microshock therapy to stabilize nerves during trauma. Controlled pulses reduced tremors and helped maintain motor control. This technique became the basis for compact stabilizers used by field medics, allowing treatment to continue even in chaotic, high-pressure conditions. Chapter 66. An engineering division built ultralight bridges from modular carbon rods. They tested how weight distributed across triangular grids. The structures held more load than expected, helping teams deploy temporary crossings quickly. The project revealed how geometric balance often beats heavy materials when speed and mobility matter. Chapter 67. A covert ocean mapping group studied cold water chimneys, vertical streams rising from deep vents. They learned these columns move heat rapidly, affecting sonar reliability. Understanding this allowed more accurate underwater scanning, preventing misread targets caused by shifting thermal layers invisible to standard sensors. Chapter 68. A physics lab explored how rotating magnetic fields spin liquids without direct contact. They observed vortex patterns forming instantly. This technique became useful for mixing sensitive chemicals without contamination. The simple idea, moving fluid with magnetism, opened cleaner methods for preparing field-ready compounds. Chapter 69. A drone program tested feather-like stabilizers inspired by birds. These tiny flaps reduced turbulence during sharp turns. Early trials proved natural aerodynamic tricks outperform many mechanical solutions. The research helped create agile reconnaissance drones capable of precise movement in tight urban spaces. Chapter 70. A behavioral study tracked how people react to faint background tones. Subtle harmonics influenced focus and stress levels. The team learned certain frequencies boost task performance without subjects noticing. This shaped covert audio environments for long-duration, monitoring rooms where mental stamina matters. Chapter 71. A materials group tested ceramics reinforced with microlattices. These internal grids absorbed shock by channeling force sideways. Even thin samples survived impacts that shattered standard plates. The research guided the creation of lightweight armor panels for vehicles and drones, proving structure matters as much as raw strength. Chapter 72. A covert atmosphere project tracked how volcanic ash drifts over long distances. Using laser mapping, researchers learned fine particles form layered sheets in the sky. These layers bend signals unpredictably, affecting communication lines. The findings helped design backup methods for high-altitude operations during natural disruptions. Chapter 73. A chemical unit explored ultra-fast bonding agents. These liquids hardened in seconds when exposed to carbon dioxide. They were tested to seal cracks in equipment during missions. Although unstable for public use, the idea inspired rapid repair kits that rely on environmental triggers rather than heat or pressure. Chapter 74. A sensory research team studied how humans detect extremely low vibrations. Subjects stood on platforms that shifted subtly. Tests showed people sense rhythm changes before amplitude changes. This insight improved early warning systems that alert personnel during structural failures, using human sensitivity as a calibration reference. Chapter 75. A biology project examined desert beetles that collect moisture from air. Their shells use tiny ridges to trap droplets. Engineers copied this pattern to design portable water harvesters for dry environments. The concept turned natural adaptation into a silent tool that gathers drinkable moisture without external power. Chapter 76. Engineers tested shape-shifting alloys that bend when heated. These metals returned to their original form after cooling. Trials proved useful for self-adjusting clamps and compact devices. The technology later supported rescue operations where equipment needed to deploy automatically under specific temperature conditions. Chapter 77. A classified optics group studied ultra-thin mirrors that flex like membranes. They controlled curvature with electrical charges, adjusting reflection in real time. This created sharp images even with vibrations. The research influenced telescopes and surveillance units that needed clear visuals in unstable environments. Chapter 78. A neuroscience project explored how brief flashes of light reset circadian rhythms. Volunteers exposed to controlled pulses showed improved alertness during irregular schedules. This helped design light-based tools for personnel working across shifting time zones, aligning internal clocks without heavy medication. Chapter 79. A mechanical team built silent gears coated with special polymers. These materials reduced friction noise, allowing machinery to operate discreetly. The findings supported equipment used in environments where sound reveals position, proving small surface changes can create major tactical advantages. Chapter 80. A data retrieval project tested crystal memory layers that stored information through light patterns. The crystals held data even under extreme temperatures. Though expensive, they inspired future high-resilience storage for missions requiring secure, durable archives that survive conditions where standard drives fail. Chapter 81. A covert engineering team tested silent cooling systems using liquid nitrogen microchannels. Instead of fans, thin tubes carried cold gas through devices, removing heat without sound. The method kept sensitive electronics stable during long missions. Though complex, the concept proved temperature control can be achieved quietly with precise fluid flow. Chapter 82. A marine physics group studied how sound bends near underwater cliffs. They discovered steep walls act like acoustic mirrors, redirecting signals over long distances. This helped refine sonar mapping, preventing false readings caused by overlapping echoes. The findings improved navigation in deep zones where ordinary scans become unreliable. Chapter 83. A biology lab researched fast-adapting moss that survives extreme dryness. Scientists learned the plant enters a dormant state, reviving instantly when exposed to moisture. This mechanism inspired compact moisture indicators for sealed containers, providing a simple visual warning when internal humidity shifts unexpectedly. Chapter 84. Engineers examined how microsprings behave under constant vibration. Some designs resisted fatigue far better than predicted. Their durability made them ideal for stabilizing sensors on aircraft and high-speed vehicles. The project highlighted how small mechanical parts often determine the reliability of entire systems. Chapter 85. A covert communication unit explored coded light pulses invisible to the human eye, but readable by sensors. They used narrowband wavelengths that passed through tinted surfaces. This created silent, line-of-sight messaging for operations where radio waves risk detection. The concept blended optics with encryption. Chapter 86. A geological lab studied rapid soil liquefaction. Using vibration rigs, they simulated shock waves and watched how moisture caused sand to behave like fluid. The results improved structural reinforcement techniques, helping facilities remain stable during sudden seismic events. The research connected basic soil mechanics to large-scale safety planning. Chapter 87. A medical team tested micro-oxygen injectors that deliver tiny bursts of concentrated O2 to support breathing in thin air. Early prototypes extended physical performance at high altitude. Though small, the technology provided backup for missions where oxygen levels drop unexpectedly and time becomes critical. Chapter 88. A covert robotics group explored insect-sized machines powered by light. Mini solar cells allowed continuous operation near windows or outdoor areas. Their small frames moved using microlimbs modeled after ants. While limited in strength, these robots offered silent observation in environments too tight for traditional devices. Chapter 89. A physics team studied how heat radiates in vacuum chambers. Without air, temperature changes occurred through direct infrared emission. By mapping these patterns, researchers improved thermal coatings used on satellites, ensuring surfaces stay stable when cycling between extreme cold and intense sunlight. Chapter 90. A psychology project tracked decision accuracy under limited information. Participants made rapid choices using only partial data. Results showed people rely on pattern familiarity rather than full context. This guided training programs that teach personnel to identify key details quickly, improving reaction speed during high-pressure scenarios. Chapter 91. A covert physics team tested ultra-thin vacuum balloons made from layered films. These spheres held shape without internal pressure, floating when heated by sunlight. Though fragile, they offered silent, long-duration observation at high altitudes. The project showed how temperature differences alone can create lift when materials are engineered precisely. Chapter 92. A sensory research unit analyzed how humans react to faint electrical fields. Volunteers stood near low-power coils while completing focus tasks. Some fields improved concentration, others caused mild distraction. The findings shaped workspace designs for mission control rooms, reducing invisible interference that affects mental clarity over long shifts. Chapter 93. An engineering division developed compact shock absorbers using magnetorheological fluid, liquid that stiffens under magnetic force. Tests revealed near-instant response times. These systems allowed vehicles to adapt to rough terrain smoothly, improving stability during high-speed operations where mechanical delay could compromise safety. Chapter 94. A classified wildlife project tracked birds migrating across magnetic anomalies. GPS tags showed their routes shifted slightly when magnetic fields fluctuated. Understanding this behavior improved predictive models for drone navigation, helping systems correct course when passing through regions where magnetism disrupts standard compasses. Chapter 95. A cryogenic lab explored how metals behave at extremely low temperatures. Some alloys grew brittle, while others became surprisingly tough. This data guided the construction of equipment used in polar zones and high-atmosphere missions, ensuring materials stay reliable when exposed to extreme cold. Chapter 96. A secret underwater project tested flexible cables filled with gel to absorb deep-sea pressure. Unlike rigid lines, these cables compressed gently, protecting internal wiring. This innovation supported long-term monitoring stations located in trenches where standard equipment fails under crushing force. Chapter 97. A neural tech unit studied how quick eye movements signal hidden stress. High-speed cameras captured tiny shifts before subjects responded verbally. These micro-movements revealed cognitive load, helping create tools that assess alertness in real time, valuable during missions where silent monitoring is crucial. Chapter 98. A propulsion team explored mini thrusters powered by rising steam. Heated water triggered rapid bursts, pushing small devices forward. Though simple, the system worked reliably in wet or humid areas. This low-tech propulsion inspired tools used for mapping confined spaces where traditional engines pose risks. Chapter 99. A materials lab investigated dust-resistant coatings for desert equipment. They discovered that slightly charged surfaces repel fine grains, keeping machinery clear during storms. This solution protected sensors and optics, preventing critical failures in harsh environments where visibility and airflow drop rapidly. Chapter 100. A final classified project examined how weak gravitational shifts affect precision tools. Using suspended instruments, researchers tracked tiny drifts caused by local mass changes. The data improved calibration for sensitive devices used in tunnels, bunkers, and spacecraft. Even small gravity variations proved important for accuracy in high-stakes operations. Those were 100 glimpses into the secret work shaping modern technology. Quiet projects, big impact. If you want more deep facts and unseen discoveries, make sure you stay tuned. Thanks for watching. Until the next story behind the curtain.